We are talking about lesson 12, which is solving inverse variation problems. Back in lesson 8, we talked about direct variation. Obviously, they're just inverses of each other. With direct variation, as a review, as x increases, so does y. As x decreases, so does y. The ratio of y divided by x is a constant. Well, inverse variation is just going to be the inverse of that. So since these two are both going in the same direction, these two must not be. So as x increases, y is going to have to decrease. As x decreases, then y has to increase. Well, how are we going to find our constant then? Now our constant for these, if you remember, is the letter k. How do we find k? Over here we were dividing them. What's the inverse of that? We're going to multiply them. So x times y gives us our constant. Okay, if we look at our data set here, what is this going to end up being? Well, there are a couple different ways to look at this. First of all, if we look at our x's and our y's are going up, our y's are going down. That sounds like inverse variation to me. But we got to figure out what the constant would be. Now, we're going to have to do something to figure out what that constant would end up being. If we look back here at this equation, x times y equals k. Well, if we multiply those, and k is the same for every single one of these, then this is going to be an inverse variation with whatever that constant is. So 1 times 8 is 8. 2 times 4 is 8. 4 times 2 is also 8. So since these are all the same, this does have to be an inverse variation problem. Is this equation an inverse variation? Yes. If so, what is the constant? Well, the constant has to be 8 here. If we were to go back and fill in this blank, well, 8 times what would also give us 8? Well, that's got to be a 1. And if you look at those, that looks, as x is going up, y is going down, it looks like it's just an inverse of each other. With our bottom question, what will the y value be when the x value is 16? Well, we could add 16 onto the end here. And we could do this 2 different ways. If we look at this, this is always doubling as it's going up. This is always getting cut in half as it's going down. So half of 1 would be 1/2. So I'm thinking right away that that's 1/2. Is there another way to do it? Sure there is. We can look. We've already said that this is an inverse. So our inverse equation is x times y equals k. All right, we know that our k for this whole situation is 8. And we know that our x value is 16. We just have to solve for y here. So we're going to divide both sides by 16. And y has to equal 1/2. For this one, 2 different ways to do it. Okay, the first way we did it based on patterns. Not always will that pattern be so obvious. The second way will work every single time. For this one, determine if the data set shown represents an inverse variation. All right, so first thing I'm looking at is I'm looking at my data. X is going up, y is going down. It's possible then. All right, so it could be an inverse variation. We just got to figure out if the constant is the same for all of them. For inverse, that's when we're multiplying x and y together. So 2 times 6 is 12, 3 times 4 is 12, 4 times 3 is 12, 5 times 2.4 is also 12. All right, so since all of these were the same, then this is an inverse variation problem. All right, what is the constant? Our constant is 12. Say, for example, though, that this was not a 2.4, say it was a 2.6. This would then be a 13, which would mean these are not the same. Now this is not an inverse variation problem, and we don't have a constant that's held true here. All right, so be very, very careful of this. Make sure you multiply them all out to see that they're all the same. All right, moving on to the next one. if we look at this, one of the things, if x goes up, y has to go down. Y is not going down here. So this is not an inverse variation problem. Say the question was, though, tell me what kind of variation this is. Well, it's not inverse. The only other way that we know is direct. All right? So we would have to find another way to do it. For the inverse, though, remember, you can always multiply your data sets together. So before we go to the direct, let's look at that. 3 times 6 is 18. 4 times 8 is 32. Those aren't the same. So that's another way to tell that it's not an inverse. Let's see if it's direct, though. All right, going back to our first slide, it said that for direct, that you could find the constant by taking y divided by x. So let's take y divided by x. 6 divided by 3 is 2. 8 divided by 4 is 2. 10 divided by 5 is 2. 12 divided by 6 is 2. If this asked what kind of variation is this, you would say that this is direct variation with a constant value of 2. All right, this one doesn't say that, but if it did. All right, next one, a couple of word problems here. The number of revolutions per minute varies inversely as the number of teeth in the gear. If 50 teeth result in 150 RPMs, what would the RPM be if the gear had 20 teeth? Well, first thing that I see is I see varies inversely. And that tells me, all right, we've got to multiply x and y together to get our k value. What's x and y? You get to decide. I'm going to say that x is t and y is RPMs. All right, so now I'm going to use the first information that I got to be able to come up with my k value. Well, teeth is 50, RPMs is 150. If we multiply those together, we should get our k value, which 50 times 150 is 7,500, which is our k value. Now we can use this and our next set of data to be able to solve for what we're looking for. So, x is 20 teeth. Y, we don't know. Y stands for RPMs here, and that's what we're trying to find. So we just leave it as a y. Our k value is 7,500. So then we divide both sides by 20, and our y value is 375 RPMs. All right, going to the next one. The number of students in every class varies directly with the number of dodgeballs. For one class, there are 12 students and 8 dodgeballs. If in another class there are 28 students, how many dodgeballs are needed? Now there's two different ways to do ones that are varies directly. Varies directly, you can set up proportions with this. Varies inversely, you cannot. Alright, so if you wanted to, you could say, well, 12 students for every 8 dodgeballs equals 28 students for every X dodgeballs. And then you could cross multiply and solve that. So let's do that really quick. We multiply these together. We take 28 times 8, and we get 224. 12 times x is 12. So 224 divided by 12 gives us 18 2/3. Well, how does that work? We can't have 2/3 of a dodgeball, at least we shouldn't have it. So, how many dodgeballs are needed to have their proportion? We would have to round this up, wouldn't we? Alright, so this would end up being 19 dodgeballs. Alright, the other way to do it, remember that k would always equal y over x. And for this, I'm going to say, well, I'm going to have my y as dodgeballs and my x as students. So then k would equal dodgeballs over students. Simplify that down, that's 2/3. So k equals 2/3. So then I would use my k value and my 28 students. So 2/3 equals y, which was dodgeballs, over 28. And then I've got to solve for y here. So 28 times 2 divided by 3, look at that, we still get 18 and 2/3, which still needs to be rounded up to the 19 dodgeballs. Alright, next page. Last one that we have here is we have what's called joint variation. Joint variation is simply where you have 3 variables, and one of them depends on changes in the other 2 variables. Alright, you can have this set up as what I have written down here, k equals z over xy. Really what this is this can be any combination of one variable over the other 2, or 2 variables over 1. Problem with this one is you have to figure out what combination has to go where here, and I'll show you that in just a second. Is the equation d equals rt an example of joint variation? How many variables do you have there? We have 3 variables here. So yes, this would be joint variation. Why? Well, first of all, because we have 3 variables, and one of them depends on the other 2 changing. Alright, if we were to look at this as rate equals distance over time, well, isn't how fast you're moving dependent on how far you're going over the amount of time it takes you to get there? Yeah, so this would be an example of joint variation. So your y, you would just put that into a sentence then. Alright, does the data table below represent a joint variation? We've got x, y, and t. Alright, well, first thing we gotta do is we gotta figure out, well, what variables are gonna go where? Well, let's say that we did x, y over t here. So for our first one, we'd have 4 times 1 over 2. 4 over 2 is 2. For our second one, we'd have 16 times 2 over 4. 16 times 2 is 32, divided by 4 is 8. These have got to be the same for this to work. So this is not the way to do it. And that's what you're gonna have to do with this, is you're gonna have to guess and check on these to figure out what the right combination is. So I'm gonna say, well, let's try x over yt. So then I've got 4 over 1 times 2. Well, 4 over 2 is 2. And I've got 16 over 2 times 4. 16 over 8 is 2. 36 over 3 times 6. 36 over 18 is 2. And 64 over 4 times 8. 64 over 32 is also 2. All of these are the same, so this would be the equation for it. So what's the constant? Our constant here is 2. So yes, this is joint variation, and it has the same constant of 2 for all of those. Alright, next one. These have to do with a couple little twists to it. Does the equation v equals as squared represent joint variation? Well, one thing I haven't said is, well, what happens if you have an exponent? If you have any exponents in there, it is not variation. There's no variation to it, okay, because it doesn't stay in the same pattern with it. So this is not joint variation. what variation does the equation y equals mx plus b represent? Well, for every single one of them, it was always multiply or divide. I've got a plus sign in here. Whenever you have a plus or a minus in there, there's no variation to this either. So, what variation does this equation represent? None of them. Alright. Last one. The number of runners in a 5K varies jointly with the number of runners in a 10K and a marathon. Alright, that sentence is very important here. Alright, varies jointly. Varies jointly. That means that to find our constant, we're going to take the number of runners in the 5K, because that's first, varies jointly with the rest of it. Because the 5K is out in front of this, that goes on top. On bottom, the number of runners in a 10K and a marathon. So on the bottom, it's going to be the number of runners in the 10K times the number of runners in the marathon. And that's going to give us our constant here. Alright, if 5,000 runners are running in the 5K, 100 in the 10K, and 25 in the marathon, how many marathon runners would go with the 100 running the 5K and 10 running the 10K? Lots of numbers up here. We need to use our first situation though to be able to solve for our constant here. Alright, so we're going to use this equation. We've got 5,000 runners running the 5K over 100 runners running the 10K and 25 running the marathon. Well, if we simplify this down, we've got 5,000 on top, 2,500 on the bottom. 5,000 divided by 2,500 is 2. So our constant for this situation is 2. Alright, and then we've got to use our bottom situation here. We want to figure out how many marathon runners there are here. So, using our same equation, our k is 2, equals how many 5K runners do we have? We have 100 over how many are running the 10K? We've got 10 here times m. Well, there's our equation. We just got to solve for m now. So I want to get rid of this. I want to get rid of the fraction. I'm going to move all these over here. How I do that is I multiply both sides by 10m. And then on this side, those go away. On the left side, we have 20m equals 100. Solve for m, divide both sides by 20. We've got 5 runners running the marathon in this situation. Alright, that's how you figure these out. Pay attention to where the varies jointly is at in your problem, just like with varies directly and varies inversely. Any questions? Please let me know.